Math 1314, Tyler Junior College, Section 2.5, Transformations of Functions. Horizontal translations, or shifts. In the previous video, we identified the transformation you make to a function that causes its graph to shift up or down. In short, add a number at the end, graph moves up, subtract a number at the end, graph moves down. It's natural to follow through and ask what causes a horizontal translation. I will tell you that it is still addition and subtraction, but unlike a vertical translation, to invoke a horizontal translation on a function's graph, you don't add or subtract at the end of the function, you add or subtract inside the function directly onto the x. For example, f of x equals quantity x plus 2 squared. Now this plus 2, we're over at the end, graph moves up 2, end of story. But when you add or subtract directly to the x as opposed to the end of the function, that invokes a horizontal translation. All that remains now is to figure out which direction, left or right. Well, if I told you that this plus 2 caused a horizontal move, which direction would you think it would go? To the right or to the left? You would probably say to the right, because 2 is positive, and then the x-axis positive is to the right. But watch what happens if we sketch this manually. What do I mean by manually? I mean inserting values and connecting the dots. Let's start with the original 3 x coordinates I have labeled here, -1, 0, and 1. And then if necessary, we'll substitute some more values. We'll just talk this through. If I substitute -1 into the function, -1 plus 2 is 1, and 1 squared is 1. Right away we have a problem. If this moved to the right, then this point would land over here. And there wouldn't be a point at -1, 1. Let's get some more evidence. If we substitute 0, 0 plus 2 is 2, 2 squared is 4. If we substitute 1, 1 plus 2 is 3, 3 squared is 9. Okay, let's just plot these points real quick, roughly speaking. -1, 1 is still about here, but 0, 4 is up here somewhere. 1, 2, 3, 4. And by the time we go over 1, we're already way up 9. Where is this parabola? Let's get some more evidence, because I think it might be over here to the left. So we need a number less than -1, so let's try -2. -2 plus 2 is 0, 0 squared is 0. -2, 0 is a point on my graph, so right about here. Yeah, this looks like it's moving to the left, but let's confirm it one more time by substituting one more number to the left, -3. -3 plus 2 is -1, -1 squared is 1. -3, 1 is a point on the graph. That would be back here, and now I think I see where the parabola is. So the 3 points that were here have now been relocated to -3, 1, -2, 0, and -1, 1. So it looks like the graph should have moved to the right, but it actually moved to the left. The reason is sort of a balancing move. For example, consider the origin. Where will this point wind up? Well, in order to get 0 out of the function, the inside of this has to be 0. 0 squared is 0. In order for the inside of this to be 0, I need the opposite of that number. So I have to look to the left of 2 to find the number that cancels out with +2. And using a similar but not quite similar argument, we can justify that all the points actually move to the left too. So adding a number directly to the x does invoke a horizontal translation, but it kind of does the opposite of what you expect. If you add a number directly to the x, it actually causes a translation to the left, and vice versa. If you subtracted a number from the x, it would invoke a translation to the right. So to get a parabola that moves to the right, this would have to be a -2, not a +2. Unfortunately, that's counterintuitive as opposed to the vertical translations, which are fairly intuitive. Add goes up, minus goes down. But With the horizontal translations, you add or subtract to the x and you get the opposite of what you would expect. So, here's the summary for horizontal translations. If g of x equals, now how do I say add an x directly to the x in an original function? Well, you go inside and say f of x plus c. If I add a number directly to the x to create a new function, then the graph of g of x is obtained by translating, and again, the word translating is synonymous in this context with shifting, obtained by translating the graph of f of x, the original function without the plus number, translating the graph to the left c units. So if you add a number to the x, you go to the left, and vice versa. If g of x equals f of x minus c, meaning that you had a function that was one of these, but you walked up to the x, tracked parentheses around it, and subtracted a number from it, then the graph of g of x is obtained by translating or shifting the graph of f of x, the original function without the number subtracted from the c, to the right c units. We're still working under the assumption that the c is positive, so when it says plus, it's really an addition problem, and when it says minus, it's really a subtraction problem. So for example, let's say I ask you to sketch the graph we'll say f of x equals the square root of x minus 3. You would have to ask yourself two questions. What's the shape and what do I do with it? From the square root function, we know that the original graph, before anything happens to it, starting at the origin, is the top half of a parabola that opens to the right. But what transformation does the minus 3 on the x invoke? Not down 3, it would have to be out here to go down 3. A minus on the x invokes a translation to the right. So we would go to the right 3. So an answer, and you don't have to draw it super accurately, I would just keep track of relevant points like where it starts. Instead of starting at the origin, it would go to the right 3, start here at 3, 0, and then I would sketch the graph. If I wanted more precision, I could track down more points, move them all to the right 3. So to summarize, adding or subtracting a number directly to the x invokes a horizontal shift, but it kind of does the opposite of what you expect. Adding to the x moves it to the left, whereas subtracting from the x moves it to the right.